All right, good morning. Sorry for the delay. Y'all can hear me okay?
Yes, sir.
All right, thank you. So, a few reminders. Oh, let me look at one of the questions in the chat. Yeah, if you're doing a percent error calculation, you get 0 sig figs on top, then the answer is 0. Okay. Don't forget exam 4 is on the 19th. Scope quiz is due on the 10th. Get it done by, you're going to have to get it done by 5 p.m. Tyler will be here tomorrow. So if you're coming in tomorrow, he will be here. You can do the scope quiz tomorrow. I'll be around today. Unfortunately, I do have a 1:30 meeting, but Tyler will be here too. And both of us will be here on Wednesday. And we've got quite a few students get the scope quiz done on Friday, which was good. I was happy with that. Okay. The chapter 30 homework is due on the 12th. Biot-Savart law is due the 10th. Thursday is a holiday. So I'm not going to have student help hours on Thursday because it's a holiday. And so if you have questions, I'll be here on Wednesday. Okay, you can ask your questions on Wednesday. You can come see me because I'll be on campus. Okay? But yeah, and I'll probably send you, I'll remember to send you an email regarding Thursday. So Thursday we won't have any student help hours. But I'm going to make myself available most of the day on Wednesday. Okay? So today what I'm going to do is talk about the force on a wire and the magnetic field again. I'm going to talk about Ampere's law and Faraday's law. Okay? Hopefully I'll have enough time to get to Faraday's law. I do want to do a demo because I never got a chance to do it regarding current carrying wires. So I need to plug something in first. Hold on a second. I have a coil of wire right here. These coils of wire, and we're going to talk about them today, are called solenoids. So I have a solenoid, and I hooked up power to it. So it's going to produce the idea is it's going to produce a magnetic field, and I want to show that to you. I want to demonstrate that to you. I will demonstrate that to you by having a compass near it. Maybe let me magnify this a little bit so you can see it better. So here's the compass. Okay, this is the compass needle right there. Okay, so I'm going to I'm basically going to turn the power supply on and off very quickly because I'll blow the fuse on this power supply. I don't know if you guys saw it move. Let me try it again. Do you folks see that compass move? Okay, so what that tells you is that this current carrying coil of wire produces a magnetic field. And if I put something magnetic like iron inside it, you would see a more pronounced effect. Because when you put the iron in there in the magnetic field, the iron then becomes a magnet too. Okay, so I just want to demonstrate that to you so you get to see, you get full justification how a current carrying wire produces a magnetic field. All right, let me go back. Seems like the left side of the board looks blurry.
It's always a little blurry,
It's
but
always a
it's
little
okay.
blurry. Okay. All right. So we talked about the Biot-Savart law, and we did some problems, and we derived a couple of equations. We derived the equation for the field due to a long wire. That was equal to mu naught I over 2 pi r, where r is how far away you are from the wire. Okay, I did the problem by doing a finite size wire, and then I took the limit as the length of the wire goes to infinity. I also did it for a loop of wire. And we got mu 0 I over 2r. These are pretty common systems, okay, that hopefully you'll get to remember them. I'll probably have the equation on the exam, but you should try to remember those, at least by the exam, because those are pretty common ones. I mean, unless I have you derive them. Okay, I'll put them on the exam unless I have you derive them. So I want to consider two long wires placed near each other. I'm going to draw them in different colors. I'm draw a red one, carrying current I to the right, and I'll draw a blue one, carrying current I to the right. They're both going to be producing a magnetic field. And I want to consider the force of one wire on the other. So let's look at the top wire. It produces a magnetic field. What does the magnetic field look like for the top wire? Well, if I use the right-hand rule, I point my thumb in the direction of the current, my fingers will curl this way. So out of the board on top, but into the board below. So this wire, the blue one, is experiencing a field into the board. Okay? So we want to use the equation F equals IL cross B to calculate the magnetic field on, the force on the blue one due to the red one. Well, since these are long wires, F is infinite. The length is infinite and the force is infinite. So what I want to do is calculate, instead, I want to calculate F blue over the length of the blue wire. Okay, that's really what I want to calculate, but I want to calculate the magnitude of it. Now, the current is this way, the magnetic field's into the board. These two vectors are perpendicular to each other, so this is just going to be I times B red. In fact, this is the blue wire. Now, what is the direction of the force on this guy? Well, let's see. Let's draw a picture. Let's draw a right-handed coordinate system. I is this way. The magnetic field's into the board. if you use the right-hand rule, you point your fingers in the direction of I, curl them towards the magnetic field, your thumb points upward. So the force is upward. So now what's the magnetic field due to the red wire? Well, it's going to be given by this equation. And so this is going to be I blue, and then B red is going to be U naught, I red, over 2 pi. And let's call the separation between these two wires D. So this force is mu naught, I blue, I red, over 2 pi times D. Now what about the force on the top one? What about the force on the red wire? What do you expect it to be?
Equal and opposite.
Yeah, equal and opposite because of Newton's third law, right? What does that tell you about the wires then? If this force is down and this force is up, right, if the force on the red one is down and the force on the blue one is up, then they attract each other, right? So when the currents are in the same direction, they attract each other. And just for fun, let's take a look at the force on the top one. Let's just look at the direction. So the magnetic field due to the blue wire is out of the board above it, and into the board below the blue wire. So in this particular case, we want to find the force on the red one. Maybe I should draw these in color. If I use the right-hand rule, point my fingers in the direction of I, curl them towards the magnetic field. I got to flip my hand around. My thumb points downward. So this force is downward. So the force per unit length of the red one is equal to the same thing, but it's downward. Okay. Questions on that? Generally, we don't write it in terms of blue and red. What we do is we'll call this one, the top one, I1, and this one, I2. I use blue and red so we can tell the difference between them on the board. And so in general, when you write the expression for the force between two wires, it's given like the force per unit length between two wires is given like this. And you should be able to derive that. If you can't memorize it, you should derive it because it comes from two equations. It comes from this one and this one. So all you need is these two. If you know these two, you can derive this equation. It's really easy. Okay? What if the currents are in opposite direction? What happens if the currents are in opposite direction?
Changes the direction of one of our fields, one of our magnetic fields.
Yeah, well, the direction of the magnetic field will change, but what will they attract or repel? If, let's say I flip this over. If I flip this over, then the current is going to be in the opposite direction. The force that used to be pointed up will be pointed downward. And if this feels a force downward, this is going to feel a force upward because of Newton's third law. And so they're going to repel each other. So if the currents are in the opposite direction, they're going to repel each other. If they're in the same direction, they're going to be attracted to each other. What if we set the current in both wires to 1 amp? If you set the current into both wires to 1 amp and you set D to 1 meter, what do you get? If you make this one and this one, what are we going to get? You have 4 pi times 10 to the minus 7 Tesla meter per amp times 1 amp times 1 amp over 2 pi times 1 meter. This comes out to be 2 times 10 to the minus 7 newtons per meter. The force per unit of length would be this value. This is something you can measure. In fact, we do a lab, when we're on campus, I do a lab where I have you measure the force between two current carrying wires. So here's the thing, if you set the distance 1 meter apart and you adjust the current, so this is the force between them, then you know you have an amp in the wires. You can use this to define the amp. The device which does this is called a current balance. Okay? A device that does this is called a current balance. And the lab we would do if we were on campus, it would be the current balance, and I'd have to measure this quantity. Okay. Let's do another example with force between wires. Suppose this time I have a wire and a loop. A rectangular loop or a square loop. Circular loop, it would be a very difficult problem. So here's a current carrying wire, I'll call it I1. And then I have a rectangular loop. I'm going to draw everything in black this time. Let's call this distance, I'll use a different color for the distances, D. D plus A, so this dimension's A, and we'll call this dimension L. Okay? I want to calculate the force on this loop of wire. Now, we talked about this in the previous chapter. The force on a current on a loop of wire in a uniform field is 0. It is not 0 here. And you folks did a worksheet for the force on a loop of wire in a non-uniform field, and you had to set up some integrals, etc. I'm going to try to do this without setting up integrals. Why can I do this without setting up any integrals? Well, in order to do this problem, I got to find the force on this one, this one, this one, and this one. What can I say about the force on these two wires?
The force gets weaker as we move further away.
Yeah, it's weaker as you get further away. But in terms of the force on this one and the force on this one, what do they sum up to be?
Oh, zero.
Zero, right? They're going to add up to zero. They're the same wire. They just have currents in the opposite direction. So I don't have to worry about these two. I only have to worry about these two. And you're right. This top one is going to experience a larger force than the bottom one because it's closer to I1, the source of that force. And in this particular case, I don't have to calculate the force per unit of length because this thing is not infinitely long. I can calculate the force on that wire. And I'm going to use the equation to calculate the force on this one and on this one. Now, what do we know about this one? These two are going to be attracted. So the force on this wire is going to be upward. But these two are going to be repelled from each other because they have currents in opposite directions. So I know that the total force is going to be easy. Right, the force on the top wire minus the force on the bottom wire.
Professor.
That's it.
Professor.
And I can factor things out, I guess.
Professor, may I ask a quick question?
Yeah.
I think you just said this, but why is it minus top minus bottom, not top plus bottom?
Oh, because they're in opposite directions.
Oh, okay. So it is plus, but because they're in opposite directions.
Yeah. I okay. Maybe I should do it like this.
Yeah. Thank you.
Is that okay?
Yeah, that makes sense. Yeah, thank you.
Okay. Because yeah, you're used to summing forces, right? Okay, so this is straightforward. Yeah, but what if I wanted to find the force of this one?
You need an integral for that one.
Yeah, so I'd have to break this up into oh, what did I forget? I'm missing something from there. What am I missing from there?
L.
Yeah, I'm missing L. Sorry. Right, because I don't have to calculate the force per unit length, right? Because this thing is not infinitely long. Okay. So anyway, going back to this, I'm going to call this a d. I'll just call it dy. And then I need to use this equation. Right, I need to use this equation, and I got to integrate like you did on the worksheet. Okay, but these guys are perpendicular to each other, so I can really write it like this. Get rid of the vector symbols. And my dl is really y. And I just got to integrate, since these are distances, right? In this equation, this is a distance, right? It's not a coordinate. It's really the square root of something squared. So it's really a distance. And so then F is going to be the integral from d to d plus a of mu naught, and I keep forgetting the, no, we're fine, of mu naught I1, I2, over 2 pi dy over y. So you can calculate the force on this one, and it's logarithmic. And if you do the force on that one, the cross product will be in the opposite direction. You'll get them to cancel out. Okay. So no more practice with setting up this integral. Questions on this one? So I'm going to do a couple more miscellaneous things before I move on. Suppose I have
Actually, Professor, can I ask a quick question?
Yeah.
Why are the bounds from, oh, it's from D to D plus A. Okay,
Yeah,
okay, sorry, that makes sense.
Can you erase it then?
Yeah, you're good, thank you.
So I want to do the following. I have 3 long wires. And they are in the form of an equilateral triangle. Okay, hold on a second. These wires have currents coming out of the board. This wire has current going into the board. I want to find a force on that wire. What do I do? What do I do? What's the first thing I do? Let's see how you remember certain things. I want to find the force on this one due to these two. What's the first thing I want to do? Anybody? What do I have to draw? It's a force problem.
Free body diagram?
Yeah, that's the first thing I do. If it's a force problem, I got to draw a free body diagram. I want to find the force on this one due to this one, and the force on this top one due to the one on the left. And so let's consider these two. These two are going to repel each other. So the force is going to be this way. These two are going to repel each other, so the force is this way. What can you say about the total force on this one? Which direction is it?
Up.
It's straight up because the x components cancel. And the reason why is because this is an equilateral triangle. All the sides are equal to each other. So this distance and distance are equal to each other, and the currents are the same. Like I said, I probably wasn't clear in specifying that. Okay, so you'll have problems in the homework where you're going to have to find the force on a bunch of parallel wires. And so the first thing you got to do is draw a free body diagram, and then consider whether or not they attract or repel each other. And you're going to use this equation to find the magnitude of the force between them. So this is like a Coulomb's law problem, except it's with wires. Okay, so be aware you're gonna be doing problems like this. Are we okay with that? No questions? Okay, let me do another one. This is a little bit different. Suppose I have a wire with the current coming out of the board. And I want to determine the magnetic field at this point P. It's a long wire, so I can use this equation. Which way does the field point?
To the right. Right. Towards P. No.
Remember, the field lines
points
circulate,
upwards.
right?
And now it's cold.
I'm sorry, say that again.
Points upwards at P.
It's going to be this way, right? This is not a point charge. This is a wire with current coming out of the board. Use the right-hand rule. The field lines are going to form circles. That's too high. Hold on a second. I gotta change that. I have to draw too big a circle. Let me make point P a little bit closer. So the field lines are going to form circles, right? This is supposed to be a circle. And the magnetic field circulates around like so. And so at point P, the magnetic field is tangent to this point, and so the magnetic field points like that. How do I find the direction of the magnetic field at this point?
It's still tangent to the circle, right?
It's tangent to that circle, right? Like this. So you can draw a radius vector for that field line, because whatever that distance is, and then you draw a tangent line to that radius vector. That'll give you this direction. And if you're given the coordinates of this point relative to the origin, then you can figure out that direction. Let's say this angle was 30 degrees. If this angle was 30 degrees, then you can figure out this angle. And you do have problems like that in the homework. That's why I'm bringing this up. Okay, these field lines for the long wires are going to form circles, and you need to figure out what is the magnetic, how do you get the direction of the magnetic field anywhere along the circle. The magnitude is easy because you just got to plug it into this equation. But how do you get the direction? How do you get the x and y components? That's a little bit harder, but you just got to realize it's the direction is tangent to the field line. Does that make sense?
I think it does. I do have a quick clarification question, though. When we are finding the magnitude of B, would we use the top equation?
Yeah, for a long wire.
Okay.
Yeah, you
So
use
if
this,
the current
this is for,
was,
I'm sorry?
if the current was in a loop, then we would use the bottom one, right? It's not if the field is in a loop. If that makes sense.
Well, this one's for a loop of wire.
Yeah. Okay. I just wanted to make sure it was the wire that's in a loop, not the field.
Yeah. So this is for a loop of wire. This is for the magnetic field due to a long wire. This is the force between two long wires.
Okay. Yeah, I'm just making sure. Thank you.
Okay. Actually, not two long wires. Oh, the force per unit length for two long wires. Other questions? Okay. So there's a bunch of homework problems in the assignment for chapter 30 where you have to consider these things. And they're discussed in the book, but I thought I'd highlight them. So suppose now we have a long wire carrying current again. And you know already that the field lines form circles around this long wire. Okay, by the right-hand rule, the field circulates like this. The value of the field anywhere on that circle is the same, right? Because it depends only on how far away you are from the circle, from the wire, sorry. Suppose I integrate the magnetic field around a closed loop, that loop. I integrate the magnetic field along the path, the red path you see there. Its radius is r. I'm integrating in the direction of the magnetic field. Of course, then this dot product will be positive. By the way, the magnetic field is in the theta hat direction. You guys learned the theta hat direction in Physics 205. And dl is also in the theta hat direction. So this dot product is 1. And this dl is basically an arc length. What does this come out to be? Well, this is for a long wire, so I can put this in there. What does this integral come out to be?
R's will cancel, the 2 pi's will cancel. U naught I.
So just get mu naught I, right? It turns out that this is true in general. The result of that integration is true in general when it comes to magnetic fields, and this is called Ampere's law. And it's kind of like the Gauss's law equivalent for magnetic fields, because I can use that to calculate magnetic fields for systems that have a lot of symmetry. Now, in order for me to prove that, I have to use, in general, I have to use vector calculus. Okay, so I can't do that here, so I'm assuming you will believe me that this is true in general. Okay? And it's an important theorem. Not theorem, but an important law. Okay. Now, it turns out that the surface that's defined by that loop, well, it's open, right? It's an open surface. Why should the loop care about what kind of surface it encloses? Right? I mean, it doesn't matter what kind of surface this thing encloses. this thing is valid. And of course, if you use vector calculus, you'll see that right away. But I have to discuss this here because the reason why, and this is an important thing, because I'm going to use this idea later on. I have a video I need you to watch when we get into the next chapter regarding Ampere's law. Okay. Really, the fact that the current penetrates an open surface requires us to say that this equation is true for any surface enclosed by the loop. That current's penetrating a surface. Okay? Whether the surface is the planar surface or a surface maybe that looks like this. Okay, whatever surface is attached to that loop, this thing is going to penetrate it. So it doesn't matter what is the shape of the surface enclosed by that loop. Okay, and this is because, and this is a vector calculus theorem. It comes from a vector calculus theorem. But physically, you can understand that for any current that penetrates this loop is going to penetrate whatever surface is enclosed by it. Okay, so this equation is true for any surface enclosed by the loop. And I will say this, that this is valid as long as the current is time independent. I has to be time independent for this to be true. The way it is written right now. If the current is time dependent, we can find a way that violates this last item here. You'll find a way where it's not true for any surface enclosed by the loop when this is time dependent. And the video that I want you to watch talks about that. And it turns out that we have to add a term to this. Okay, we actually will have to add a term to this guy in order for this to be true for any type of current. But right now in this chapter, all our currents are time independent. And so all the problems we'll be doing in this chapter, this will be valid for all the problems we do in this chapter. Okay? So again, the big stipulation is that this has to be true for any surface enclosed by the loop. Okay, and that comes from a theorem of vector calculus.
So what is it that this result is describing? Like, what is Ampere's law telling me?
Well, it tells you that the magnetic field circulates. If the field lines form closed loops,
Okay.
it curls. I mean, from a vector calculus point of view, there's something called a curl associated with it. I don't know if you had Calc 3.
Most of it, but
Yeah. So this is a measure of the fact that the field curls. It circulates. The electric field does not. And so when you integrate the electric field around a loop, what do you get? If you integrate the electric field around a loop like this, you get 0. That's a big difference. So that's the big difference between electric and magnetic field. Okay. So it's a description of the property of the magnetic field, that it forms closed loops. In fact, this is a measure of the circulation of the field. And there's another way to write it. And it has to do with something called a curl in vector calculus. It's analogous to Gauss's law because we can use this expression, this law, to calculate magnetic fields for systems that have a lot of symmetry. Remember, the current I is the continuous current passing through any surface bounded by the closed path. In order for us to use this expression to calculate a magnetic field, we need a very high degree in symmetry. It's more restrictive than the symmetry requirements of Gauss's law. In order for us to use this to calculate a magnetic field, the magnetic field has to be constant over the loop. And again, the fact that the integral is not zero is characteristic of any vector that has a rotation. It curls. Okay? All it does is it tells us that a vector has a tendency to rotate. So I want to use this to calculate the magnetic field for a couple of systems, just for a couple of examples. So I'm going to write down Ampere's law here. Suppose I have a thick wire. Okay, so I'm going to give you two views. So the current is going this way. The current is coming out towards us. Let's assume that the current density is uniform. The amount of electrons passing through any point here it's just the same over any part of the cross-sectional area. Remember that if the current density is uniform, is this. If I is not uniform, then di is the current density dA. Okay, so I want to apply this law to this problem. I want to find the magnetic field inside and outside the system. So I'm going to make a weird kind of approximation. I'm going to assume mu inside here is the same as mu outside. Okay? I'm going to assume mu inside equals mu outside. I mean, it's going to be off by a factor, really, inside, but that's okay. And you'll see problems like that in the book. So in order for me to use this, I got to consider the magnetic field, what the magnetic field looks like. No matter where I am inside this wire, let's say some distance r from the wire, the magnetic field is going to have the same value on that circle. But it's going to depend on how much current is enclosed in here. Okay? So this I is the I that's enclosed in the loop. Okay? All right, so let me write down Ampere's law. I want to find a field inside. The field, I'm going to integrate in the same direction of the magnetic field. So if the current comes out like this, I'm going to integrate this way so that my dot product is positive. So this is going to be B times R times d phi. But then I need to know how much current is enclosed in there. How do I figure out how much current is enclosed in there? How do I figure out how much current is enclosed in there?
So we have to integrate from 0 to R.
Okay, so I have to integrate J dA from 0 to whatever that R is. Well, what is J? It's the current density. So it's the current, since it's uniform, it's the current over the area of the wire. So this is I over pi r squared. And the area of a circle, my element of area is 2 pi r dr. So what does this integral give us? One of the pi's cancels. Isn't this going to give us r squared over 2? What is this integral? It's 2 pi r times b, and that's going to be equal to mu naught I r squared, or big R squared. Solving for b, get mu naught I r over 2 pi r squared. So inside the wire, the magnetic field increases linearly with r. What about outside the wire? Outside the wire, I choose a loop. Like so. And again, I'll integrate in the direction of the magnetic field. And again, I'm going to set up this integral. This integral is always going to end up being 2 pi rb. But when I integrate for my current, how much current is enclosed inside my big loop? How much current is enclosed?
All of it.
All of it. which you should expect, right? Because it's the field due to a long wire. So outside is this, inside is this, and so when I plot it, then the field looks like the following. So B on the vertical axis, R on the horizontal axis. This increases linear. And if you plug in little r equals big R here and big R here, you get the same value. So it's continuous and decreases as 1 over r like that. That's what it looks like. So outside the wire, it's always going to look like this. But inside the wire is going to depend on what your current density looks like. In the homework, you have a current density that's not uniform. And so you'd have to write the current density as a function of R and then integrate it. Kind of like what you were doing for Gauss's law. But I think mathematically these are easier to do. It may be harder to visualize conceptually what's going on. Okay. And by the way, be careful with this dot product, right? If you're integrating opposite the direction, if the field and the current are in opposite directions, then and you're integrating opposite the direction of the field, then this dot product is negative. If you have a loop of wire, if you have two wires, and you set up a loop around those two wires, when you integrate this, the total current that penetrates that loop is 1 amp. Okay, because the one dot product, when you take the dot product with one, it's going to be positive. When you take the dot product with the other, it will be negative. So this will be 1 because you have currents going in the opposite direction. If you have, for example, a wire that does this, and then integrate around here, what's this integral going to be equal to?
Is it going to be 0?
It's going to be 0, yeah, because the current goes in one direction, it comes out the other direction. There's no current enclosed. It doesn't mean there's no field, right? It might not necessarily mean there's no field.
When you say the current, there's no current enclosed, that's the net current?
Correct. That's the net current that's enclosed. Yeah, so that integral, just like Gauss's law, when you integrate around a closed surface that represents the net charge, this represents the net current enclosed by the loop. Okay? All right. So I'm going to do 2 more examples. I want to do something I call a solenoid. A solenoid is a coil of wire. You see them in your car. You see them used. I don't know if you ever used the like a sprinkler system. You have the sprinkler system electronically turn on. They all have a coil on them that once it's activated, it makes a magnet move and make electrical contact. Okay. But those are short solenoids like this one. This is a solenoid. Okay. The solenoid I want to talk about is long. Its dimensions are long compared to its diameter. I want to look at that one. And I want to use Ampere's law to calculate the magnetic field due to a solenoid. Okay. So let me try to draw a solenoid. Kind of like in your slide. I have a bunch of wires all the way around it. Remember, this is long. The length is way bigger than the diameter. I exaggerate the diameter so you can kind of see what's going on. Okay, so I'll make the current come out here. The current go here. And I made these big. These should be the same size as those. Sorry. If you use the right-hand rule, you curl your fingers in the direction of the, you point your finger in the direction of the current, you'll find that the magnetic field inside kind of goes in this direction. Along the axis, it's in the x direction. Off the axis, it's a little bit off. It has a y component, and maybe a z component. But the longer you make this and the narrower you make this, the other component gets smaller and smaller and smaller. And the magnetic field is essentially in the x direction, and it's fairly uniform. And of course, the field lines can come out of this long solenoid and do this. I want to use Ampere's law to calculate the magnetic field everywhere. Let's look at outside. Since I think the magnetic field outside will point in the x direction, I'm going to choose a rectangular loop. I mean, it's pretty clear that outside the field is going to point in the negative x direction. So if you have a field that points essentially in the negative x direction, what is the dot product between this dl and this field line?
0.
And the same thing with this one, right?
Yeah.
But this dot product is not necessarily 0 for each one of these, because we don't know what B is, right? And I can do the same thing below. Because I know below the field lines are going to wrap around kind of in the opposite direction this way. And so when you take this B dotted with this dl, this is not 0, actually, or whatever it is. It's not necessarily 0. And I can do the same thing for the top ones. But these vertical ones, it is. But we know that these two have to be in opposite directions, because how much current's enclosed in there? How much current is enclosed in this loop?
None.
None, right? Because if I'm up here and the current's down there, there's no current enclosed in this loop and there's no current enclosed in this loop, right? Okay. So there's no current enclosed in this thing. So we know that this integral is 0. But we don't know what each one of these two terms is. We know that the sum of those two integrated over the lengths have to be 0 because they're in opposite directions. So,
Professor,
yes.
is the top one supposed to be going to the left? The top arrow.
Oh, yes.
And then may I ask you a quick clarification?
Yeah.
How did you know that was the direction of the current? Did you use the right-hand rule to get that?
The direction of the current, direction of the field.
The direction of the, I believe it's current on the.
Well, the
Ampere.
current, I just assumed that direction for the current.
Oh, okay.
But for the field, it's based on what I said what the current was.
Yeah.
Okay.
Okay.
Because I could have chosen the current in the other direction to set this up. But the direction of the current, it doesn't matter for this example. All I've established is that the magnetic field is uniform. But I don't know what the value is. What happens if I go further and further away from the solenoid? What happens to that what should happen to that magnetic field?
It's gonna go down.
It's going to go down. So if I applied Ampere's law down here, it's going to be uniform. So this kind of doesn't make sense, right? Because this says that the magnetic field is uniform, but if I go down here, the value goes down, right? In fact, what if I make this Amperian loop, if I make these legs infinitely long? What must this be then?
Is it going to approach 0?
It's going to approach 0. So if this one approaches 0 and the field's uniform outside it, isn't this 0? So the magnetic field outside of this thing is 0. Again, we're assuming this is a long solenoid. In reality, a real solenoid, the magnetic field is not 0. It's small, but it's not 0. If you have a short solenoid, the magnetic field due to a short solenoid, like this one, it looks like the magnetic field due to a bar magnet. Okay, but as this becomes longer and longer, the magnetic field outside gets smaller and smaller. So, because we can make this thing as big as we want, we can say that we can show that B is 0 outside the solenoid. Okay. Now let's choose another loop. Let's choose this one. Let's choose that loop. We know the field is 0 out here. So if I want to calculate, I got to integrate over this one, that one, and that one. We know the field is 0 along this one, so that one does not contribute. These two are perpendicular These two are perpendicular to the magnetic field, so they don't contribute. But this one is not. And this is going to be equal to what? Well, it's going to be equal to mu naught. How many wires get through this? How many wires penetrate? Well, let's say n wires. And each one carries current I. And this was just going to be B times L. So the magnetic field is mu naught N over L times I. N over L is the number of turns per unit length. So just mu 0 N times I. Question? Did you have a question or? Oh, okay. That's it. That's the magnetic field due to a solenoid, and it works fairly well, that approximation. So, in your notes, I've done a problem where I calculate the magnetic field due to a solenoid. Let me show you the problem. I've done, in your notes, just basically has extra problems where I calculated things. So oops. Just give me a second here. I actually calculated the magnetic field due to a solenoid, and I was fairly, I mean, I made only one approximation in this. So this problem is solved in your notes. And what I want to do is look at, so I calculated the field due to one loop, and then I generalized to many loops. And I found the field along the axis. So you can read through it, but I wanted to show you the graph of the magnetic field along the axis. Give me a second here. This is what the magnetic field looks like along the axis. When the length over radius ratio is huge, look at how constant the magnetic field is. So these are all in your notes, as opposed to when L over R is 10. So the greater that ratio, L over R, the more uniform it gets, and then the more we get the approximate result, mu naught Ni. I mean, even at L over 100, even at L over R equals 50, it's quite good. It's quite uniform. Okay. Otherwise, if you have if L over R is 10 or less, it's like the field due to a bar magnet. Okay, let me get out of that. So anyway, if you look at your notes, I've done several problems which are probably the more complicated versions of ones I did in class, and I put them in there for you guys. So you may want to take a look at them, the two examples. One's a solenoid, and the other problem I did in your notes is one we did on Friday. This one we did on Friday, except we did it out of the plane. Actually, no, we didn't do this on Friday, did we? I'm going to do this one. Let me do this one before we finish. I did this with the other group. I'm sorry. I'm going to do one more with you, two more problems with you guys today. Okay. As a review, I guess. Let me do one more Ampere's law problem, and then I'll go back and do this one. I completely forgot we missed that one. But in your notes, I do one where it's out of the plane of the board. So when I did the solenoid problem, I assumed that the wires were tightly wrapped. There's no space between the wires. And of course, if I make the wires thicker, that's going to affect my approximation. Okay? If I have a thick wire the problem becomes much more complicated if I have a thicker wire, or let's say I have a lot of insulation around the wire. Okay. So then the approximation becomes invalid. Another one I want to do is kind of like this, except I take a really long solenoid and I actually make it into a closed circle, into a donut. Let's call it torus. Or a toroid. I want to look at the field with a toroid. So there's a donut-shaped body, and then the wire is wrapped around the donut. Okay? So you have a wire like this, but it's tightly wrapped. All the way around. And what does that do? If you use Ampere's law, here, there's no current. And in fact, there's no field here. If you use Ampere's law out here, the total current that's enclosed is 0. So you get no field here, no field here. The total field is inside the torus, and it's along the axis of the torus. So the magnetic field does this. At some distance r. Okay, let's call the inner radius A. And outer radius 2A. Okay, so this is the body of the donut, our torus. I'm going to choose a loop in the direction of the magnetic field. And this is how much current is enclosed inside my loop that goes in the direction of the magnetic field. Well, the magnetic field is uniform along that loop. It's the same value. So this is B times 2 pi times whatever the radius of that circle is. And then how much current is enclosed? Well, it's going to be, it encloses all the loops. every loop of wire that goes around the red loop counts as a current. So we solve for B. And the magnetic field is approximately given by that expression for the torus. Okay? So that's another example. Let me go back and do one more problem, because I skipped this on Friday. So I want to do one more Biot-Savart problem for you guys. And then I'll be done. I guess we didn't get to Faraday's law. So I want to use the Biot-Savart law to solve this problem. Okay? So let me go back to what we did on Friday. And Biot-Savart law allows us to calculate magnetic fields due to current carrying wires. And we did the loop, we did the circular loop, we got this expression, and we did one that was 1/6 of this, so it just 1/6 of this value. Now I want to do this particular problem where I have a current carrying wire. There's actually 3 wires here. Remember to follow the process in doing these problems, right? Figure out your ds, your r hat, your r squared, and put them into dB, then integrate. Okay? But we've done the loop, and we've done the wire. Can you tell me what the field should be at the center here? This is a circular, semicircular, okay, even though it doesn't look like it. Can you tell me what the field is like over there? How much work is going to be required by you to figure that out?
Is that going to be half of our loop formula?
Half of this one?
Yeah.
What about these two? What can you say about those two?
The field of the origin is parallel to the current in those two.
Oh, okay. So that means that. So what are you saying? What's 0 in this equation then?
The cross product.
Yeah, the cross
For
product
those
is
two
0.
segments is 0.
Yeah, so ds cross r hat equals 0 here, and ds cross r hat is 0 here, but it's not. So you're right. It's going to be half of this expression. That's it. Okay? So if you notice that ds cross r hat is 0, and right away, I mean, that makes the problem very simple. But you're right, the current is in the same direction as r hat. And so that cross product is automatically going to be 0. When you do the worksheet, you have a problem where you have that. Okay. All right, good. Any questions? Because I'm done with chapter 30.
Yeah, so that was kind of my question. I just wanted to make sure that we can do all the homework tonight, and it looks like we can.
Yeah, you have everything. Because I'm done with the chapter. That's why I spent a little bit of time doing the problems with the wires in the shape of a triangle. I wanted to go over that, and then finding the field for a current carrying wire at some arbitrary point P. That's why I went over that too, because a lot of times, sometimes the books don't go over that, but the field line, the field is tangent to the field line, and that'll give you the direction of the field. So I spent a little bit of time going over that so that it can help you with the homework. So yeah, you have everything you need to do the homework now. Okay.
Okay, and then is the worksheet due Wednesday or is the worksheet due Friday?
Wednesday. You can do that one first.
Okay, so and then the homework is due Friday?
Yeah,
Ah, okay.
yeah. I changed all the dates. They don't show on Canvas because every time for it to show on Canvas, I have to upload all the assignments from WebAssign onto Canvas every time I change something.
Yeah, no, I did not. I thought I was going to start the homework tonight, which I probably will, but I would do the worksheet first if it's due first.
Yeah, yeah. And that'll help too with it'll make the homework pretty easy then because most of the BOs of our problems in the homework are pretty straightforward.
Okay. And then you'll be available after this, before 1:30, for me to take the scope quiz, right?
Yeah, yeah. Or Tyler. I have a short meeting at 1:30, and then I have a meeting at 3. But otherwise, I'm available.
Okay.
If
Yeah, no,
you-
I'm gonna come right now so I can hopefully catch you.
Okay, that sounds good. All right, so we'll see you guys on Wednesday then.
Well, thank you.
Sure, no problem.
Thank you.